Hello and welcome to Lab 2, Lines of Charges. The purpose of this lab is to estimate the charge required on each tape in order to float one above the other. This goal is similar to the goal of our first lab, except now we must distribute the charge evenly across the length of the tape in our model, rather than measure it as a single point charge. In order to create this model, we will use GlowScript to create a computational model in addition to our data from Lab 1. For a quick preview of results, the charge from Lab 1 using the point charge was found to be 4.207 times 10 to the negative 8 coulombs, whereas the charge found in Lab 2 using the line of charges method was found to be 1.332 times 10 to the negative 8 coulombs. For the physics principles involved, we have Coulomb's law, Newton's second law, and the force of gravity. Coulomb's law measures the electric force of attraction or repulsion between two separate charges. Newton's second law tells us that the net force applied to a system is directly related to the system's change in momentum, and the force of gravity is the attractive force between any two objects. Looking at our data from Lab 1, we found that the charge on one piece of tape was found to be 3.765 times 10 to the negative 9 coulombs. And here is some of our data about the tape we used, including mass, length, and width. Similarly to our last lab, we are going to use the gravitational force, the electric force, and the charge of the tape in order to find the charge of the singular piece of tape. So first we calculate our gravity to be 1.991 times 10 to the negative 3 newtons, which we can then equate to the magnitude of the electric force, since they cancel each other out as the floating tape is at rest. And then we can plug this in using, since we know that the electric force is equal to the electric field using the rod formula times the charge. And so then we can plug in all of these variables to solve for our Q, which we found to be 1.332 times 10 to the negative 8. And here for our GlowScript model, we first plug in our observed values, including the mass of the tape and the estimated net charge that we found in Lab 1. And then next, we will edit these values to create a function for the electric field. And then here in this top one, we use this to calculate the line charge calculations using this formula down here at the bottom. And then for this bottom section of code, we do this to calculate, since we're using basically a bunch of different little point charges across the tape, this sums all those together and calculates everything for us. So here for our final results, this white up arrow is symbolic for the electric force. This yellow down arrow is the force of gravity. This blue line is our bottom tape, the red is our top tape, and then these green up arrows is our electric field created. So for this lab, we needed to make some assumptions. These three included that both pieces of tape have the exact same charge, both pieces of tape have uniform charge distribution, and that we can ignore air resistance on a moving object. Some possible sources of error in this lab include human error when we were measuring the distance that the tapes began to float, as we were just using the naked eye, which is not that precise, as well as the loss of charge that was caused while handling the separate pieces of tape. So next, what if you had modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. So when we do this, we find that our point charge value is equal to 4.7 times 10 to the negative 8 coulombs, and the line charge value is 1.332 times 10 to the negative 8 coulombs. So the reason that these differ is that these estimates differ due to the fact that the line charge calculation is a more precise measurement. This is because it uses many different segments of charge along the length of the tape to calculate the charge, which is more realistic than calculating it as a singular point charge.